first minute, I'll let Srividya set up the whole thing, and
yeah, okay.
I will give an introduction.
Okay, thank you.
Professor Apriya, you can start. I have started the recording. Yeah.
Okay. So today's con talk is about single photons and entangled photon sources by Dr. Tanmoy Chakraborty. Tanmoy did his PhD at IISER Kolkata, experimentally working on quantum correlations and magnetic field induced effects. And then he did his postdoc at Dortmund, dealing with quantum register formed using a nitrogen-vacancy center and various manipulations of that. I think all those things were based on NMR technology. And afterwards, he joined QTech at Delft, and there he has been working on experimental implementation of a frequency multiplexed quantum repeater scheme and quantum networks which can implement those kind of things. It's upcoming experimental scenario where all these things will be very much useful, and he is going to tell us some things about it. Nowadays, he also has a appointment in Singapore together with a university at, not university, QTech at Delft. So over to you, Tanmoy.
Thank you very much, Professor Patel, for your introduction, and it's a great pleasure to talk in Quantox. So I will mainly present our experimental results, which I have been working on during my postdocs in Dortmund and QTech in TU Delft. So I will focus on mainly two kind of single photon sources. One is NV center in diamond, and another is a parametric down conversion source, which is based on nonlinear optical processes. So to start with, I will give a brief outline here. So first I will talk about our some basically pulse sequences which we developed to generate a pure state by polarizing the electronic and nuclear spins of NV centers. So two methods, one is polarization transfer and another is population trapping. Next, I will talk about characterizing ensembles of NV center and then imaging charge states of NV center. And then in the next part, I will talk about our frequency multiplex single photon source and a demultiplexer, which basically demultiplex all the spectral modes onto distinct spatial channels, and then single photon spectroscopy and joint spectral measurements, and then the optical interface between our frequency multiplex source and the rare earth ion doped crystal, which will be the quantum memory basically for our quantum repeater scheme, and then another hybrid quantum network project where we are trying to create optical interface between photons, single photons generated by NV center and SPDC generated photons. So first, I'll start with NV center in diamond. So basically, in this project, we have been dealing with a single NV center. So we had the diamond substrate, and the diamond substrate had basically all the NV centers embedded in it. And then if one can choose a single NV center which is magnetically well isolated from any other centers, then the electronic and nuclear spins associated with that NV center can be considered as a quantum register. And then by addressing the population of those spin states, basically the quantum state engineering can be performed through designing pulse sequences which contains optical, microwave, and radio frequency pulses. So for most of these quantum information protocols or quantum network protocols, it is necessary that we start with a high initial purity of the initial state, and then we basically continue with our quantum operation. So this enhances the signal to noise ratio and the fidelities of these quantum processes. So this project basically focuses on deterministically enhancing the purity of a certain quantum state by polarizing the electronic and nuclear spin associated with a single NV center. And then I will talk about characterizing ensembles of NV center, which will have basically applications in quantum sensing technology and also imaging charge states of NV center. So to start with, just a quick introduction about NV center. So this is a point defect center in diamond where one carbon atom is replaced by a nitrogen atom, and then there is an adjacent vacancy where the carbon atom is missing, and they form together the nitrogen vacancy center. This is a nice quantum system because of its high coherence time at room temperature, and many quantum experiments can be done at room temperature itself. So to study, and also it's a single photon emitter. So this is a typical Hanbury, Brown, and Twist interferometer, which basically measures the anti-bunching, and one can see that it gives us single photons. It's basically one can generate single photons on demand, so it's a deterministic source of single photon. And now to start with, what do? We basically load our diamond system onto a confocal microscope, and then we scan over the diamond substrate, and then go to a particular bright spot, which might be an NV center. Then we start with the initial experiments. First, we measure the anti-bunching and see if we are having the anti-bunching dip less than 0.5 or not. That assures us that, okay, it's a single photon emitter, but it could be NV, it could be other single photon emitter. Then we basically do the spectroscopy and then measure the spectrum and see the zero phonon line if we are having or not. Then if we see the zero phonon line for NV centers, then we understand, okay, there is this fluorescence, NV has contribution into this fluorescence. Then we move forward to the ODMR and other measurements to basically use that NV for our experiment. And so in the first experiment, what did we do? We basically choose...
Can I ask a question? Sorry.
Yeah, sure.
Yeah. So in your previous slide, so sorry, I missed the initial part, but so the D2 correlation that you are showing, so the dip is about, I don't know, like 0.4 or something.
Yeah.
So what's the source of this? Like, why is it so large?
So it basically, ideally it should reach 0, but if it's single photon emitter, then it's less than 0.5. So it should be in somewhere in between 0.5 and 0.
So my question is, why is it not very close to 0? I mean,
so here I would say the signal from NV is basically pretty low, and then we are splitting it in through some beam splitter, and then there are some fiber couplers. So we are working with very low signal, and in that regime, the dark count from the detectors dominate, and also there is some stray light coming. So all these stray light and the detected dark count also almost come
it's
to
the background. So okay.
Yeah. So that basically uplifts the diff.
So you don't use any filter, is it?
Here we have a band plus filter which is kept around the zero phonon line, so that also reduces the signal a bit.
Anyway, okay.
Yeah. So in the first experiment,
sorry, I have a question from the same slide.
Yeah.
So you were talking about this being a deterministic source of single photons.
Yeah.
Can you give us an idea of the sort of repetition rates and the reliability of such a source?
Yeah, so it like as a single photon source, it can have applications wide applications in quantum network, for example. So there have been groups which have used this NV center as single photon source, and that single photon they have widely applied in quantum network for example. So for creating network node,
I'm asking specific numbers on the repetition, like the brightness of such sources, like NV centers.
Yeah.
How many photons per second can you get out? Like, you know, this kind of number is useful for how fast you can run your quantum circuits and how what is the key exchange rate in communications. So what kind of counts per second are we thinking?
So here basically when we are just measuring, when we are sending a green excitation part, depending on the setup, we can have around 100 kilo, like 100 kilohertz count rates or 100,000 photons per second. But now when we are using it as a deterministic source and we want to get the single photons on demand and we want to exclude all the phonon sideband, then one needs to use a resonant laser pulse. So this laser pulse is at 637 nanometer, and then the count rate becomes really less. So then some other basically methods have to be done to enhance the readout efficiency, collection efficiency, and other things. But for this experiment, we just used a green pulse, and the count rate was around 100 kilohertz.
Okay, thanks. There is another question from the audience.
Yeah.
Hello.
Yes.
Yeah. So in continuation of that question asked by Mr. Kaushik, I think. So you said that this the dip in the G2 measurement is not going to exactly near to zero because there are some sterlite in while doing the experiment. So so if I basically subtract the coincidences that is basically coming from the background light, so does it after subtracting the coincidences does it reach the zero value like?
Yeah, ideally it should reach almost zero. But this analysis I haven't done. So generally when people get, well, this also could be calculated if we know the dark counts and then without the dark count how much coincidence, and then ideally it should go close to zero.
Yeah, that basically confirm whether the whether the counts are whether the photon are singles
No,
or
if
they are
you
basically.
Yeah, if you have it in the range of 0 to 0.5, then it's already, you know that it's single photon, because for 2 photons, it will be ideally 0.5. So that's already a confirmation. But now to get to 0, one needs to do maybe some post-processing and see.
Yeah.
Sorry, I didn't get it. So how are you going to subtract the background?
So if you have the dark count, basically, one needs to do some kind of post-processing. I haven't done it personally, but I did it for some other experiments, for example, some cross-correlation experiments. So it will be possible to do basically. Or one can also measure basically I don't know, but maybe one detector, like without blocking one arm of the beam splitter, measure the coincidence and then do the same on the other side and then see what is the dark count coincidence on the both side and then try to calculate somehow. So
I don't still see how it is possible because but anyway, I think it's okay. We can proceed. Yeah.
Yeah. Okay, so our first experimental, our system is basically a 2 qubit system where a vacancy electron spin 1 is coupled with a nitrogen nuclear spin, which is also spin 1. So if we level the eigen spectrum, it's a 9-level system, and we basically performed the spin manipulation through these 9-level systems. So in the beginning, what we did, we basically used a long laser pulse, which is around 5 microsecond long. And what does this laser pulse do? It basically initializes the system to the bright state, which is electronic spin 0 state. So after this long laser pulse, we have a fully polarized electronic spin state. And then we apply these to microwave pulses and then adjust this electronic spin transition. After that, we apply 2 pi pulses to address this nuclear spin transition. And then after this set of 4 pi pulses, we end up with a configuration where the nuclear spin, which is the 0 spin, is fully polarized, but now the electronic spin is completely depolarized. So through these pulses, basically we have transferred the polarization from electronic spin to nuclear spin. Now we have to reinitialize the electronic spin, and for that we are basically optimizing our optical pumping process. So here we are applying a laser pulse, and if we now again apply the laser pulse with really long duration, then again it will fully polarize the electronic spin, but at the same time it will also depolarize the electronic spin. So we have to optimize the direction such that we have an optimum polarization for both the spins, electronic and nuclear spin. To calculate this, we basically formulated a rate equation model where we leveled the population of all these 9 levels through a population factor P, and formulated a redistribution matrix, which basically determines how under the effect of optical pulse, the population will be distributed among these 9 levels. And then we solve this rate equation model using the initial state before this laser pulse, and then we obtain the solution for all these 9 population as a function of the duration of this laser pulse and Ks and Ki, which are the pumping parameters for the electronic and nuclear spin, as if these two are the free parameters. And now we performed Ramsey free induction decay experiments. We basically set the laser pulse duration to different values and then perform the Ramsey free induction decay experiments, and then measure the population of the 0-0 state, all 3 nuclear spin state. So after basically performing the experiment for many different values of tau L, what we saw that for a certain value of tau L, the population to 0-0 state is maximum. After that, keeps on decreasing. So this is what we expected, because this is the regime where basically the same way it's working as the initial pulse did. So we have to choose our the value of our pulse in such a way such that we end up with the maximum population value of the 0-0 state. This also allowed us to calculate the nuclear and electronic spin pumping rate for the first time to the best of our knowledge. And after that, we basically applied some other additional pulses to drive the population in the 0 state in the MS is equal to 0 subspace. Sorry.
Sorry, that was a disturbance. You can proceed. Yeah.
Okay.
Somebody unmuted. Yeah. You can.
Yeah. So after these 2 additional pulses, we obtained pure state in the MS is equal to 0 subspace of the system. In the next protocol, we basically applied pulse sequences and applied a method which we call like propulsion trapping. So through this method, we, instead of choosing all the 9 levels, we restricted ourselves to a subspace which is spanned by MS is equal to 0 and -1, and then applied a number of pulses to sequentially trap the population to 0-0 state. So first we implemented segment 1 and address the nuclear spin -1, the population in the nuclear spin -1 state, and did not implement segment 2, and then measured the population for different values of the duration of this L1 pulses. Then after optimizing the duration of L1 pulses, we kept this segment 1 at those optimized values, and then included segment 2, and then varied at the duration of the L2 pulse, and then again re-optimized the value of L2. And finally, after these optimizations, what we saw is basically very similar thing. So we basically formulated this time the rate equation model for 6 levels, and then depending on this initial conditions, we solved the rate equation model and then fitted with the data, and we saw good analogy with our experimental values. So this method also gave us a purity of around 78%, and the electronic and nuclear spin pumping rate Ks and Ki, which we obtained through these measurements, are also consistent with the earlier values. But here you can see that we are always limited by around 77 to 80%. The final population, we cannot go higher. And the reason is the optically induced nuclear depolarization. To study it further, what we first did, we thought that, okay, if we implement these cycles multiple times, but each time with depending on the earlier cycle, if we re-optimize in each cycle the pulse duration, and then again do the same for the subsequent cycle, then maybe we will be able to reach a higher value of the purity. So this way we could reach maybe 3-4% higher, but not more than that. Then we wanted to see that how this nuclear depolarization is basically stopping us from obtaining the high purity. So we basically plotted the simulated the population of this state as a function of the ratio of the nuclear spin pumping rate to electronic spin pumping rate, which is R, and the duration of the laser pulse. And then what we saw that when the nuclear spin pumping rate is very low, we obtain a very high value of purity, but as it keeps on increasing, we have less and less purity. And this happens both for the segment 1 and segment 2. So this ensures that the nuclear depolarization is basically the key factor, which is stopping us from achieving higher purity of the our target state. In another project in Dortmund, basically, this was a collaborative project between Duisburg and Ruhr University of Bochum and TU Dortmund. So the main goal of this project was preparing NV centers which can have good efficiency in quantum sensing applications. So Duisburg people used to grow the diamond by chemical vapor deposition. In Ruhr University Bochum, they used to perform the ion implantation, and in Dortmund I used to perform the optical and magnetic resonance spectroscopy study of the NV centers, which were prepared in Duisburg and Bochum. So some example measurements from that. Here I developed a confocal setup basically which could do the confocal scanning with the nano positioning stage integrated with the micro positioning stage. So we could basically map the whole diamond sample with millimeter dimension, but with nanometer resolution. And then we have the spectroscopy part integrated with it, so we can switch between confocal microscopy and spectroscopy. And also we have the electronic spin control part for measuring the CW and pulsed ESR experiment, optically detected ESR or ODMR experiment. And then the optical spectra showed the zero Fresnel line for NV0 and NV-. This is one of the example data. And we were also able to enhance the coherence time of these prepared NVs by using different dynamical decoupling sequences, for example, XY4, XY8, and CPMG. Now to actually apply these NV centers in quantum sensing, our target charge state is NV-, but there is in the NV center a charge state conversion process is involved, which basically happens through ionization and recombination. So it switches between NV0 and NV-, and the NV0 state is basically not of our interest, and it always creates a strong spin independent background, so that reduces the signal to noise ratio. To basically use this NV center efficiently in quantum sensing, we have to selectively choose the NV ensembles which contain NV minus centers mostly, and we have to avoid the NV0 centers. So to do this, we have to image the diamond sample and see where the NV0 and NV minus centers are distributed throughout the diamond, and then we can use that part to basically deposit our material which we want to sense. So this is why this was the motivation to basically develop methods through which we can do also the spectral decomposition and also image the charge state. So here what we did basically, we exploited the spin mixing mechanism for NV center. So when we apply the magnetic field and then change the magnetic field, all the splitting between all the Zeeman level changes, and that changes the transition rate between all these levels. So then that reduces basically the fluorescence of NV minus center. So this has been already observed. And as a function of magnetic field, if it's an off-axis magnetic field with the strength, the fluorescence keep on decreasing. But this doesn't happen for NV0 center. So we used the spin mixing phenomena for NV minus as a resource, and then performed spectroscopy at many different magnetic fields, and then extracted the signal which is solely coming from NV minus center. And this allowed us to basically decompose the spectrum for NV0 and NV minus. So we measured the spectrum at zero field, at low field, at high field, and then took the difference of the spectrum. Then we did a bit of extensive analysis to optimize this scaling parameter f. And then when we know this value of f, we can decompose the spectrum into the spectrum for NV0 and NV minus. And then we imaged the diamond substrate and separated the distribution, separated the PL signal which is coming from NV0 and NV minus using the same technique. So we first performed a confocal mapping at a lower field, then at a higher field, and then use the value of f which we determined through our analysis to separate out the signal from NV0 and NV minus. We also developed another spectral decomposition technique. So this is an optical filter based decomposition. So we chose a optical filter like a long pass filter, which has a certain spectral function basically. So it allows signal after some wavelength and stop signal before this, a regular interference filter. And then we have the spectrum for NV0 and NV minus, and then they appear in different spectral domain. So this long pass filter basically allows the signal from NV0 and NV minus with different transmittivity because they have different overlaps. So we calculated these transmittivities, and then by solving simply linear equations, we could image the signal coming from NV0 and NV minus. So this is a general method. If there are multiple spectrum available, like overlapping in an image, by choosing suitable band pass or long pass filter, one can basically decompose the signal from these different light sources. And we, to test the efficiency of this method, we also simulated the images. First, we simulated image without any filter, then with a long pass filter, and then applied these linear equations to separate out the signal from NV0 and NV minus. Now to conclude, basically through these projects, what we have been able to do, we have been able to develop two methods. One is polarization transfer method, another is population trapping method to enhance the purity of a target state. And we also have been able to calculate the electronic and nuclear spin pumping rates through our analysis. Secondly, we have been able to develop a scanning stage to map a whole diamond substrate. And also we have been able to create NV centers which can have good efficiencies in sensing applications, and we have been able to image the charge state and have been able to decompose the spectra for NV0 and NV minus using our developed method. To move to the next step, so this is about our work in Delft, what we have been performed. So I have been working there for almost 3 years. So it's basically a frequency multiplex quantum repeater scheme, and we are using a spontaneous parametric down conversion source as a single motor source in this quantum repeater scheme. So many of the quantum network experiments have already used this SPDC sources as single photon source and have demonstrated many nice experiments. For example, this first one is one old experiment from our group where they basically generated time bin and then pumped a SPDC crystal with this early and late bin, and then generated an entangled photon pair, and then stored one of the photon in quantum memory. And then after retrieving the photon, they measured the entanglement feasibility between the photons, which is at telecom at 795. And then even after storing, they saw there was a entanglement was preserved. So that was an important demonstration. And this was a recent experiment from another group where they basically used 2 independent sources and then performed 2 photon quantum interference here. And next they perform entanglement swapping and then distributed entanglement over several two of these quantum memories, which can be basically later scaled up for several quantum memories. And this is another similar kind of experiments where also they perform quantum distribution of quantum entanglement over different quantum memories. And previously also in our group in 2016, single photons generated by SPDC were used to perform quantum teleportation in a metropolitan scale. Now, so this is basically the quantum repeater protocol we have been working on. So in the heart of this quantum repeater architecture, we have a single photon source. The single photon source generates the photons in several spectral modes. So these idler spectral modes get demultiplexed here, and then they undergo frequency resolved Bell state measurement with the photons coming from another source from the neighboring link. And the signal photon gets stored in quantum memory. They get retrieved. And now, depending on which idler mode had a successful Bell state measurement, that particular, that correlated memory retrieved photon mode is basically frequency shifted to a predetermined frequency value. This is done because to achieve indistinguishability in the spectral domain with the signal photon coming from the neighboring link, such that they can undergo a joint spectral measurement here. So I have been mainly focusing on this single photon source part now, which can generate a single photon in many different spectral modes, and also a demultiplexing setup such that we are able to demultiplex each of these frequency modes onto different spatial channels with less crosstalk and high efficiency. So what we are using, we are basically using a periodically poled lithium niobate crystal, and then pumping this crystal with very high power photon, and then generating the signal and idler, which is generated following the energy and momentum conservation. But if we just do this in this way, then what we get, depending on the phase matching condition of the PPL and crystal, we get in the spectral domain only one broad spectrum, but not several spectral modes. Now but for our frequency multiplexed quantum repeater scheme, we need to generate the single photons in many different spectral modes. And to do this, what we are doing, basically, we are embedding our PPLN crystal inside a Fabry-Perot cavity. And this cavity is basically designed, coated for 1532 nanometer light, such that the single photon generated at 1532 nanometer are restricted to those particular resonant modes. Now, basically following the energy conservation, the signal modes are also appearing at the same spectral modes. Basically, we chose the length of our cavity and then the reflectivities of the coating in such a way such that we generate our single photon with a mode spacing of around 6.5 gigahertz and line width of around 40 megahertz. Now, we had this parameter, we calculated that which way should we do it, and then we basically talked with a company in Taiwan, and then they designed it. So the main goal is to create a quantum network which is alignment free and fiber coupled. So we got it designed in such a way such that we have a fiber which is pigtailed to this Fabry-Perot cavity, which has the PPLN crystal embedded in it, and then the signal and Idler photons are demultiplexed. And there is a demultiplexer basically integrated at the output of the Fabry-Perot cavity, and then we have the signal and Idler photon as output through two different fibers. Now all the spectral modes for the Idler are coming through only one spatial channel, which is just one fiber. So we have to now demultiplex each of the spectral modes and get them separated in many different spatial channels. And for this purpose, okay, so before going to that, I also say that why we are choosing 1532 and why 795. So for example, these Idler modes will go through the fiber network, and we have to choose the wavelength in such a way such that it encounters minimum loss. So this is why, in this telecom wavelength, the loss is very low. So we chose our single photon to be generated at 1532 nanometer. And also for some other quantum repeater protocols, it's required that the telecom photons are stored into a quantum memory. And erbium is a very popular quantum memory, like erbium doped lithium niobate or other host materials are already proven to be potential quantum memories. So we chose exactly 1532 such that it can match the absorption of erbium ions. And in the signal side, we are storing our single photon in thulium-based quantum memory, and thulium has absorption around 795 nanometers. So we performed the quasi-phase matching in such a way such that we generate the signal at 795 nanometer. Now to demultiplex the Idler modes, what we are using is basically a device called virtually imaged phased array. So this has never been used in any quantum optics experiment. There are some very few old literature which are available for some classical optics experiment, but never used in any quantum optics experiment. So so this is a good device when basically we want to demultiplex the light which has a bandwidth, which has a less bandwidth, but we want to demultiplex with very high resolving power such that we have very less crosstalk between the neighboring modes. So this is a diffraction grating like device which basically maps all the spectral modes in different spatial domain. So how does it work? It basically a kind of glass plate, and one side is fully reflecting and another side is around 95% reflecting. So there are some optics which has to be chosen properly at the input such that we basically tightly focus the input light onto the backplane of this device, and then it goes for multiple reflection on these two glass plates, and after each of these reflections some part of light comes out through this side, and all these wavefronts then basically are coherent with each other, and then they interfere, and then they give rise to different interference orders. So this is for only one particular spectral bond. Now if we send two spectral modes which are little detuned from each other due to angular dispersion, this will follow a little different path than the earlier one, and then they will come out through this side with a little angle compared to this one. So then if we choose now the suitable optics on this side, we are able to focus this light at different spatial domains. So this is how we are basically mapping our spectral modes to different spatial domains. So, but it has a free spectral range of 60.8 gigahertz. What does that mean? That if the input bandwidth of the light is more than 60.8 gigahertz, the spectral modes which are 60.8 gigahertz away, they will be mapped at the same spatial position. So this is how we will lose our mode purity. So we should restrict ourselves to the input bandwidth of the light to less than 60.8 gigahertz. And then we did multiple experiments by choosing different optics at the input side. So we are using different cylindrical lenses basically because we want to tune the light in the vertical and horizontal direction independently, because in the horizontal direction it's the spectral direction and it's completely dependent on the characteristics of the VIPA, how are they getting mapped, but we can control the vertical direction, and this control is necessary because eventually we want to match the numerical aperture of this light with the fiber through which we want to collect it finally basically. So so we basically used our laser and generated light at different wavelengths, and use these different sets of lenses, and then characterize, measure the mode profiles, and then optimized which cylindrical lenses we need at the input and which focusing lens we need at the output. So these are three very important parameters. Through after choosing the optimal optics, we were able to get very negligible crosstalk. So here you can see that when the frequency modes are around 5 gigahertz away, they reach the background. So the crosstalk is almost zero, and our frequency modes are around 6.5 gigahertz apart. So in this case, we will not have any crosstalk between the neighboring modes. We also end up with very high system efficiency. So this is very important because to reduce the loss into the system, because after the demultiplexing, it will undergo many other steps basically. So we should not lose the signal here much. So here we were able to get around 26% efficiency at the peak of the VIPA profile, but then it reduces on the two sides. And also by sending input laser at different wavelength and then noting down at which position they are mapped, we were able to generate a calibration curve. And then we can use this calibration curve basically to generate the spectrum for the single photon later. First, we characterized our VIPA-based spectrometer by generating an input optical comb, which is created using a laser basically. So we detuned each of these modes by 6.5 gigahertz, which equals to our the mode spacing of our source, and then we measured the intensity distribution at the back focal plane of the focusing lens behind the VIPA, and then plotted it as a function of the position of the collection fiber. Next, we send our Idler photon. We basically replaced the classical light using with the Idler signal, and then measured the intensity distribution in the similar way, and then use the calibration curve to transform the x-axis from position to frequency detuning. And this allowed us basically to generate the spectrum of our Idlers. And here basically what we did, we used a single fiber core to collect the signal, and then we moved the collection fiber. So what we measured is basically a convolution of our Idler spectrum and the fiber profile. So due to the finite broadening of the core size, we have a broadening which is due to the convolution. So we basically then theoretically generated a Lorentzian signal and then calculated this convolution to basically change the line width of the input Lorentzian line such that we match with our signal, and then the input line width tells us that this is the line width of our source spectrum. And if you remember, you also saw that we cannot send light more than 60.8 gigahertz, but here we are measuring light almost up to 125 gigahertz. So here, what did we do? We basically use a Fabry-Perot cavity filter after the Idler signal to reduce the bandwidth, because what the source generated was in the range of around 2 nanometer bandwidth. Then we used a Fabry-Perot cavity filter, which reduces the bandwidth to less than 60.8 gigahertz. Then we basically measured the spectrum first, removed Fabry-Perot cavity profile, and then detuned it, and then again measured, and then stitched those spectrum together to generate a spectrum over 125 gigahertz region. Next, we also measure the signal spectrum. Here, we basically use a Fabry-Perot cavity which is around 6.8 gigahertz wide, and then we detuned the Fabry-Perot cavity over the signal spectrum and measured the convoluted spectrum. Then we take an input Lorentzian comb and use this profile of the Fabry-Perot cavity, and then calculated the convoluted spectrum and then matched with our experimental data. So this way we could clearly say that the mode spacing is 6.5 gigahertz as we expected. Now to proceed with the joint spectral measurement, this is a simple diagram of our experimental setup. So we have the cavity SPDC, demultiplexer, then the Fabry-Perot cavity filters, and then the signal is getting detected by the photodiode, and the Idler is going through this demultiplexing setup, and then we are performing the joint spectral measurement here. So we measured the coincidences. We basically detuned the Fabry-Perot cavity filter on the signal side and kept on measuring the coincidence. So we first chose one particular Idler mode and then kept on detuning the Fabry-Perot cavity on the signal side and measured the coincidence as a function of this detuning. And then when we have the highest coincidence, we know that now we are spectrally aligning the Idler and Sigler mode. Then as a function of pump power, we saw enhancements in the coincidence rate, but G2 decreases because of multi-photon emission and other noise. Now we basically kept on detuning, kept on choosing one after one Idler mode, and then detuned the signal Fabry-Perot cavity for the signal, and then identified 20 heralded frequency modes. So we saw that when we are performing the cross-correlation measurements between the signal and Idler modes, which are energy correlated, we have very high value of cross-correlation coefficient G2. But when they are not energy correlated, there is a strong reduction. Ideally, it should be only one diagonal, and then the next value it should go to the classical limit below 2. But this doesn't happen here because of little broadening of the Fabry-Perot cavity filter there on the signal side, because it's 6.1 gigahertz. So it also very weakly allows the two neighboring modes which are appearing at the two sides of the central mode. So now with these components, we basically reach from here to here. So this is using our developed photon pair source and demultiplexer setup. This is the current frequency multiplex quantum repeater scheme, but still here we in the demultiplexing scheme we are collecting the Idler mode one after one, but for our frequency resolved Bell state measurement, these have to be collected simultaneously. So we have to develop a technique now such that we can simultaneously collect all these demultiplexed filter modes. We also have to now focus on this quantum memory side, and we have to create an optical interface between our rare earth ion-based crystal, which we are going to use for quantum memory, and our single photon source. And then we have to see whether all these components are compatible with each other or not. And this we have found from later. So here basically to simultaneously demultiplex each of this frequency mode, we developed a fiber core array. So this was a bit tricky because the spatial mapping, if you notice for each of these frequency modes, they don't have the same spacing with each other, and they follow a certain distribution. So first we measure all these distributions and then talk to the company about creating this fiber array where these fiber cores are placed exactly at this position. And now there are many different parameters, basically the input angle, the distance between the cylindrical lenses, and at which position of the VPA the input light goes through, and and then there is a the telescopic system, the distance between these two lenses, and then the 5 degrees of freedom XYZ and the angle between the angular freedom of the stage on which the fiber array is mounted. So coupling simultaneously all this fiber array was a little tricky, but finally we managed to get good coupling for these 5 modes. And when we send signals, when we set the wavelength to such a value such that the spectral modes is mapped at, for example, at this fiber core, we have very less signal on the almost zero signal on the other fiber cores. This tells that we have almost zero crosstalk, and all these cores are able to basically demultiplex with high purity of each of the spectral modes. So in this case, we have around -40 to -50 dB crosstalks. And for the single,
Tanmoy, I have a small question about your previous slide.
Yeah.
So since you have all these fibers positioned very carefully, so how does it, like when you have any sort of fluctuation, be it in your laser or in your temperature, let's say your temperature changes, then how does the coupling and the crosstalk change?
Yeah, so while characterizing, there could be some fluctuation. The laser line may fluctuate a little in the frequency domain. So this we also saw. But while capturing the Idler modes, this fluctuation will not be present because first of all, the SPDC crystal is inside a temperature stabilized box. And secondly, the resonant modes, depending on the resonant modes of the cavity, the Idler modes are appearing. So this is also fixed. So as long as our pump wavelength is frequency stabilized, the Idler mode will also appear exactly at the same spectral domain. But while characterizing, you're right, if we don't use a frequency locked laser, then there could be little broadening in all these channels.
Okay, thanks.
So now to compare with our earlier measurements, so here these are the system efficiency for all these 5 modes. It's a bit less than the signal core because of all these additional parameters and tricky alignment, but this is still good enough to give us enough coincidence to proceed with our next experiment. So in the central fiber, we have a coupling of around 17%, and it reduces to around 7 to 8% on the 2 sides. And now, in this case, we are not basically moving the core, but we are having collecting the single photon mode discretely at each of the spectrum. And here we see that when we basically use our fiber array and use one core and move it, then the peak matches with these histograms. Now, to focus on the signal side, we have been able to demultiplex each of these idler modes, and we have been able to collect those modes to separate fibers with less crosstalk and good efficiency. Now we have to also perform the frequency resolved detection for the signal modes. And to do this, the first step is to basically create a spectral trench in our quantum memory crystal, and then see if we can spectrally selectively allow the frequency mode through the trench and get absorbed all others or not. So to do this, this was a bit of experimental challenge because of we want to do everything in an alignment-free fashion. So this is still a technical thing, but it was very important, and we spent a lot of time on this. It was basically designing a mount to which we are coupling the light to our thulium-doped lithium niobate crystal. So this has to be temperature insensitive, because we will load it into the cryostat at room temperature, then cool down to less than 1 Kelvin. So we should not lose the coupling. So we had some design, and finally we came up with some design where a fiber ferrule is basically sending the light, which is going through a green lens and then coupling to our crystal. And then on the other side, we are also at the present configuration using another green lens and fiber ferrule to collect the transmitted light. And then we, for creating the spectral trench, what we are doing, we are basically using a serodyne shifting using a phase modulator, and then we are frequency shifting the light, and depending on the waveform what we send to the phase modulator from the AWG. And then we, for example, if we want to create a spectral trench of 100 megahertz, in this case, we are choosing the waveform in such a way such that we move our sideband scan through 100 megahertz in the spectral domain. So what is the concept of spectral trench? I'll just explain using this diagram. For example, we choose a lambda-like system here. So we first send light with some particular frequency with some particular bandwidth, and then transfer the population from the ground state to the excited state. Then the spontaneous emission happen, and a significant amount of population comes back to a selfing state. And this state has a high lifetime of around in the millisecond scale, or sometimes in the second scale. Then as long as this population stays in this selfing state, for that particular frequency bandwidth, if another pulse comes, it will see higher transmittivity because some of the population are already here in this state. But on the other side, on the other wavelength domain, it will see less transmittivity. So this allows us, when we align the spectral trench center wavelength with the spectral mode which we want to filter, then we can frequency selectively allow that particular spectral mode and get all the other neighboring spectral modes absorbed. So we basically created the spectral trench at the signal wavelength, signal modes, what we want to allow, like for example here, and then collected the correlated Idler mode on the other side, and then measured the cross correlation between them. So this is simply the setup. We are using all these optical switches, and we are doing lots of splicing here because this is a complicated experiment between two labs. So you can actually see it better here. So we have all the experimental setup in the photon for generating the photon pairs, demultiplexers, everything. And in the quantum memory lab, we have the preparation, the burning light, where we are using some AOM and for creating pulses, then phase modulator, some polarization control, and then all these fibers basically to basically use the optical switches and fibers to optically connect the light which is coming from the source lab. And then when the light is coming like generated from our SPDC crystal, getting frequency filtered, demultiplex, and then going through a fiber, through all this splicing and switches, and then coming back to this lab, and we are measuring, we are still having a good amount of coincidence, and we can clearly see the coincidence peak here. So then we generated the spectral trench at different frequency domain, matching with this signal spectral mode, and chose the Idler energy correlated Idler mode on the other side, and kept on measuring the coincidences. So this is how we could create this joint spectral intensity diagram. And here we can see that when the spectral modes are energy correlated, we have very high coincidence, and when they are not, the coincidence is quite less. If we now plot it in a bar plot, it will see like this. It will be like this. So if you see that when they are not energy correlated, they are almost in the classical value of 2. Now this is very important because compared to the previous experiment, what we added is our thulium doped lithium niobate crystal, and here you could see that the decrease of the coincidence without the thulium doped lithium niobate is very slow, but here it's abrupt. So this tells us that our thulium lithium niobate is giving extra spectral selectivity, and we are able to basically frequency selectively allow the mode which we want to do, which was not possible in this case because we did not have the thulium spectral filter. We only had the Fabry-Barrett cavity filter. I will briefly talk about another project. So this is about a hybrid quantum network project which was done between our lab and the lab of Professor Ronald Hanson. So the main idea is basically generating a quantum network which will connect their NV-based quantum network and our thulium ion-based quantum network. So what we are doing, we are basically the main idea is basically we generate this photon pairs, and then the photons generated at 795 nanometer get stored in thulium memory. They get retrieved, and now to perform the 2-photon quantum interference with the photon coming from NV, we need to reach indistinguishability in the pre-spectral domains, but it's at 795 nanometer. So this is why we are doing quantum frequency conversion, and this we are doing in 2 steps, because in one step, if we do, they are very close, and we need a pump of a few micrometer, which is a bit tricky. So in the first step, we are generating the light at 450 nanometer, and in this next step 450 to 637 nanometer, and then reaching indistinguishability in other degrees of freedom as well, and then measuring Hungo-Mendel effect. But to start with, instead of SPDC, we are using weak coherent pulses. So we are basically using a laser, attenuating the laser to very high degree using attenuators. Then we are using an AWG, an intensity modulator. So we are basically generating a waveform, and through intensity modulator, we are creating some pulses which mimics in the temporal domain, the temporal shape of the NV pulses, such that we have the indistinguishability in the temporal domain. And then we are performing the quantum frequency conversion, then finally measuring the 2-photon quantum interference. So this is for NV, what is being done in Ronald Hanson's lab is basically sending a resonant laser pulse, which is at 637 nanometers. So this gives NV photon with an exponential decay, and this decay time is around 13 nanosecond. So we are also, to reach the indistinguishability in temporal domain, we also send our weak coherent pulses with this particular temporal profile. So we are creating waveform using a WG and sending to the intensity modulator and creating this basically temporal pulses. And then these are signal with very low mean photon number, because NV we cannot enhance the mean photon number much, because the contribution of zero photon line in the whole spectrum of NV is around 3 to 4%. And we to reach indistinguishability in terms of intensity, we also bring our mean photon to that level for our weak coherent pulses. So that signifies that we have to accumulate these experiments over really long time, for one day sometime, if we want to do with low mean photon number. So that requires that our pulses are stable over time, both the temporal shape in the spectral domain is stable, and also the polarization is stable. So this is what we have been doing with the with our weak coherent pulses, and we got good stability. The standard deviation is around 7.2%, and for indistinguishability with the temporal profile, it was around 0.85%. And now when we reached indistinguishability between NV photon profiles and our weak coherent pulses, we proceeded with the two photon quantum interference experiment, or Hongo-Mandel effect. And when we make them distinguishable by disturbing any of these degrees of freedom, we got the G2 value of 1. But when we reached indistinguishable, we became indistinguishable in all these degrees of freedom, then the G2 value was less than 0.5. So to conclude, we have been able to demonstrate an alignment-free frequency multiplexed single photon source. We have been able to also demultiplex the spectral modes of the heralding Adler photon onto different spatial channels, and we have been able to collect all these spectral modes with very less crosstalk and with high efficiency. We still see very high coincidence with our signal. And we also have been able to frequency selectively allow our signal mode through our quantum memory crystal and measure the cross correlation with the Adler modes, which is basically necessary for our frequency multiplex quantum repeater scheme. And then when we are spectrally aligned, when the modes are energy correlated, we have high cross correlation, but when they are not, we have a strong reduction in the cross correlation value. We also have been able to show two-step quantum frequency conversion and and an achievement of indistinguishability between our weak coherent pulses and NV photons. So yeah, so these are the people who were involved in the project from QTech and TU Delft, basically for this quantum network projects, and also TNO, and from TU Dortmund and ISAR Pune from the group of TS Mohes on the NV projects. And just a few words about QTech. So it's basically a joint initiative between TU Delft and TNO. So it has mainly three directions. One is qubit research, one is quantum internet division, and quantum computing division. We were in the quantum internet division. And Delft is a very nice place to work. Yeah, thanks a lot. If you have any question, please.
Just one question on this spectrally multiplex sources. So you were talking about signal and idler, which are widely separated, right? So one is in the 700 range, other is in the telecom wavelength.
Yeah.
So how do you ensure losses and the optical coupling and all are similar for both wavelengths? Or is there any, even the fibers may be multi-mode for one wavelength and single mode for the other, and so on, right? So how do you deal with it?
Yeah, so for example, the signal strength for Adler and signal doesn't have to be the same, because they will go through many different components on the both side. For example, Adler will go through demultiplexing part, and signal will go through other Fabry-Perot filter cavities and quantum memory crystals. What we care about is the coincidence. So after all these components, if we have enough coincidences, then we are happy basically. So this is one thing. And for the fibers, we always use single mode fibers for that particular wavelength. So we have like the 795 fibers and telecom fibers, and we don't send, for example, 795 through telecom fiber or the other way around. Then it could be multimode, but we always choose the fiber we want for this particular wavelength.
Thank you. One more naive question. When you have a pump laser which has this Poisson distribution, right? So the signal and idler will they also have some Poisson distribution type characteristic? Like individually, if you measure signal and idler, will they show single photon type characteristic or?
Yeah, no, they basically don't have the Poissonian statistics. They will follow the super Poissonian statistics. So if we measure the autocorrelation, ideally we should get G2 instead of autocorrelation experiment. We don't get 1, but ideally we get 2. We also performed the autocorrelation measurements. Those are some additional experiment I haven't shown, but when we, for example, if you see here, if we send our signal through this Fabry-Barrett cavity, which allows one spectral mode, and then we add here a HBT interferometer and then measure autocorrelation, then because they follow super Poissonian statistics, we get a value of 2 of G2. Now it has a little mode impurity because this is a bit wide. As I mentioned, it's 6.1 gigahertz. It appears in between 1 and 2, but it's always more than 1. And for the idler, it's the same.
Thank you.
Yeah.
Does anyone have any more questions?
Are there any more questions? Yeah, somebody has.
Hello.
Yes.
Yeah. So for storing this 795 photon, you have used TM based, I think, some source.
Yeah.
Yeah. So in comparison to this source, rubidium also has 795 absorption, like T1 line in their absorption spectrum. So in comparison to rubidium, how like this source is, I mean, if I compare both these sources, so how, I mean, if I use rubidium instead of TM, will that add any extra advantage?
Yeah, so in this case, basically, our source is the SPDC crystal, which is a PPL, and thulium-based lithium niobate crystal we are using for storing our single photon as quantum memory. So rubidium, because here it matches the absorption wavelength of 795 nanometer, and also it has a homogeneous line width, very narrow homogeneous line width, but at the same time, all these single ions are distributed over the crystal, and they are all little frequency shifted. And when you consider the combination, you have an inhomogeneous line width, which is around 120 gigahertz wide. So that allows us to also store the single photon with narrow line width, but over a wide bandwidth. So that will allow storing many different spectral modes in this case. And the optical depth for thulium-doped lithium niobate is also quite good. Only limitation in this case is the storage time, because in this case the coherence time is quite less. So it can store in the nanosecond scale, like 100 nanosecond or something. but thulium also could be doped in other host material. For example, in our group, we are using thulium yttrium gallium garnet. So there the coherence time is pretty high. This is why the storage time is around 100 microsecond, but the optical depth is less. So these are the advantages of using thulium as quantum memory. But for rubidium, as far as I know, it has been widely used for generating single photons. But for storing, I also know that there is some protocol called Urca quantum memory. It's off-resonant cascaded absorption quantum memory, but it's mainly useful to store the single photons which are really spectrally broad. But I'm not sure if the spectral hole burning with such a narrow line width will be possible there. By the way, actually, we are also working on a protocol where we are on a quantum repeater protocol where we are trying to create optical interface between rubidium ion and thulium. So here, the rubidium will be a single photon source and thulium will absorb the single photon coming from rubidium. So we, as an initial demonstration, we already have done some experiment to show the overlap of the absorption profile of thulium with the rubidium, and we build one Doppler free absorption setup for rubidium and then saw the lines for say 87 isotopes, and then some of these lines actually has spectral overlap with thulium. So that gives us the idea that this could be optically interfaced.
Yeah. Okay. Thank you.
Thank you.
Apurva?
Okay, yeah. Okay, Tanmoy, you have answered many questions, and I
Thanks,
guess
Mark.
people who have more questions will contact you directly. That is fine.
Yeah, sure.
But,
I'll be really happy to answer.
yeah, thank you very much for this
Thank you very much.
talk, and we will remain in touch.
Yeah, sure. Thank you very much.